Hi. Been working a little while on agentic coding and finding it very dangerous. So it's been really interesting to see examples today where coding agents can make a mess. There's a lot that I agree with in both of the previous speakers. I'm hoping there'll be some overlaps and some pieces that complement it. Can I find a clicker for the slides? Sorry, thanks. So in the code review process that we were just hearing from Kristen, some folks are trying to introduce an AI reviewer. So I wanted to understand if there can be some threat models where you can have bad code getting reviewed by an AI that misses it. So I call it subverting the code review process. And we want to defend it. So I'll present a talk where I'll start with some of the red teaming, some of the bad things, sorry. And then eventually at the end, we'll turn this back on how we can use that in the favor of defensive practices. So about 7-8 years ago, I was getting a lot of luck at Akamai defending some websites, a few icons on different types of value that I've defended: websites, mobile devices, homes, and now schools. And when I was defending websites, there was a real cat and mouse game. That's part of my motivation today, to see things from the attacker's lens and to see if we can defend it. And I had the chance to work with the UK AI Safety on a concept called elicitation. Does elicitation mean something to anyone in the room? The idea that you can ask things to AI, but you think it's capable, you don't know for sure if it's capable of more than what you're getting from it. So this talk is about finding what the attackers could get from AI beyond what we get if we just ask a couple of times. Can we really see what the AI might give the attackers? It can also give defenders a lot of value. It can help us accelerate our developers. I totally agree with Kristen. If we can help our developers to get some early feedback by knowing about the design issues in their code, the security issues in their code, it's incredibly valuable. At the same time, it's not the same as a security control. We want some deterministic controls. That we could hear this from Jack Cable earlier. It's really something that makes a difference when you're using static security scans. I might have missed if Kristen already mentioned some of those, but inside of GitHub, there's a GitHub Advanced Security solution that you can use to run CodeQL rules that are very deterministic, and those can find when there are vulnerabilities. Very different from an AI looking at the code and doing some natural language processing. And we'll learn at the end of the presentation what we can learn from the adversaries to defend it. A few examples in yellow here show that there are weaknesses in the performance of an AI to perform a good code review for security purposes. We've also got some red examples that show that adversaries can use this, or there can be incidents happening with severe impacts, like the production databases that Kristen was telling us not to expose to the AI agents. Some companies found that Replit would wipe their databases, even with clear instructions. Please, it's a code freeze, but saying please, we understand, doesn't really work. So we need a threat model. So for a threat model, before we put it all in one chart, we'll just look at a few elements one at a time. The threat model starts with who's writing the code. Sometimes it's an AI now. We've got people at my company who are saying, can we get some AI-generated pull requests? Kristen was covering how we need the humans to review that. Sometimes it's also a human, and they're just inadvertently introducing a vulnerability because they don't know, or because they were under pressure. There's a lot of different reasons they might be putting some vulnerabilities into the code. They might just have bad data in the AI that they're using, and they don't notice what got snuck into the code. Maybe they're tired, multitasking. Maybe there's pressure. It can go all the way to some people taking advantage of the situation to run other things inside the network that were not authorized. I've seen everything on this list except one. I will let you guess which one it was. Ultimately, we can start with some folks working on the inside who don't know any better, and neither does anyone on the outside, how to exploit this application. Maybe they don't know, but people outside do, and they will be exploiting this. Sometimes we think that we can introduce a little bit of a backdoor, maybe for management purposes. Maybe it won't be so bad if there's some obscurity around it. We know security by obscurity won't work, but it can be a facade for us to say, we'll have this mechanism so that we can achieve whatever internal objective we have. That's pretty risky because we assume no one on the outside knows. And there are some people who might do something for someone else on the outside. For example, some of the hackers from North Korea that managed to work for some US companies last summer. I'm introducing a notion here for our threat model called genetic algorithms. I'm also curious if a lot of people already know about these. A few. Well, hi. The word genetic does not mean we're doing biology here. It actually means that we're taking two different configurations and we put them together to take the best of both. Kind of like parenting. I've got two kids and I hope that they get the better of my wife because it's not the best on my side. We get reward mechanisms because AIs try to learn through reward. And so it's interesting that we're not teaching an LLM how to be a better LLM when we use a genetic algorithm on top. We're using an LLM to generate things. In my case, it's going to be code. But we're going to be genetically changing what we ask of the LLM, meaning the system prompts, the configurations that we give to this agentic coding system can just have a variety of rule sets. And we don't know which rule sets are going to work really great. Kristen was showing the example of our LLM rules, right? The security.md file. What should we put in our security.md file? You can see that this is hopefully going to help you write good security MD files. Because with a bit of a fitness function, evaluating the performance of your rules against a variety of problems, you can select the things that work the best, recombine those, start the process again, see if there are other things that you want to tweak in those security rules. And you can do that automatically. That's the point of genetic algorithms. It's to just go and search for the solutions all by itself. If we do this, it's very different from manual review or automated review. I wanted to just introduce the concept of static rules. I mentioned CodeQL earlier, so I think I've covered this just a little bit. But what the static analysis scanners do inside GitHub Advanced Security or any other engines like SemGrep, if you're working with developers, ask them how they know that they've configured those tools well. There are different rules, and you might have some enabled, some disabled. They have very cool mechanisms like taint analysis. We don't know how much taint analysis an LLM is really capable of doing, but it certainly won't be very good if it's looking at one file at a time, because oftentimes SemGrep and other tools like this can see the bigger picture of the application and understand really holistically how the data flows through the application and what might create a security exposure. If it's powered by an LLM, we should understand that it will help developers. It will be helping them to improve, but the LLM has randomness. The LLMs are not picking the next word because it's the best word, but because it's one of the best possible next words. If you've never seen those log probs, I really encourage you to test it out on one of the playground environments with the AI providers. There's always another possible option. If you test something 100 times, you only know that it is less than 3% likely to happen. If you've never seen something happen in 100 runs, it could still be 1 or 2% likely in the future. It's called the rule of 3. So if you want to be sure that it's less than 1%, you have to test it 300 times. And the LLMs have some issues with randomness that we look at evaluations and we think, well, it's not looking too likely. We haven't seen anything catastrophic. But it depends how many tests you've run. And even Anthropic's system cards for the latest models have only tested a very small number of times each of the different test cases for very severe chemical and biological threats. The syntax. If somebody writes code and today it's secure, but they make a change tomorrow, which is no longer secure, the comments that they wrote today saying, this is secure, we've done this, we've secured or validated this input over there, might not be correct in the future, but the AI might still be influenced by the comment that says it's secure. It could also be an adversary, and in my case, that is because I'm putting the red hat, the black hat on. So if we have an input that says input format is controlled, it is validated, this is the kind of comment that somebody might leave. It could be true today, and they're running an eval function. Some of the presenters today have mentioned that we shouldn't accept any eval functions in our code. We should do that deterministically. The issue is that when I ran this question here through an LLM, this was GPT-4o mini, and the eval function most of the time comes back as vulnerable because it should be detected, but you can see the probabilities are right there if you analyze it under the hood. A probability of 20% almost that this will just not be flagged as a vulnerability. So there's a risk of influence. So putting our threat model together, how did this present a problem? We've got AIs generating code trained on bad data. It might be vulnerable already. The code review is only so likely, there's only a certain percentage likelihood that it will be detecting vulnerabilities correctly. So what should we do in our build pipelines? What should we do in continuous integration systems? We want those static scans. We want the rules to be enforced. And we want that to be enforced deterministically as something that is a hard configuration, and not pretty please LLM, can you run a scan, or remember to run the scan at the end of your review. There was great research from Redwood in 2024, I thought. There's something from 2 years ago as well. But when you have two models, one that you don't trust and one that you kind of trust, you can use the one that you kind of trust to try to supervise the other one. The problem is that the untrusted model might sometimes introduce some backdoors, which will look different to the supervisor. The problem is, where do you put your threshold to determine that you want to flag an issue is happening? There are non-backdoored examples that overlap with the backdoored examples. And so the issue of having some true positives, false positives, what is the accuracy of our system? Because we want to minimize how many times humans get escalations to go and review something if we want to accelerate our teams. So there's some challenges with this and with where we take AI safety in terms of super intelligent and catastrophically risky models. We'll make this, we'll put it all together. We'll do the genetic prompting, starting with some manual prompts. What I was able to do in Python was to just look at a few functions like this one, very similar to the one you saw before. It puts two numbers together with an eval that would be vulnerable. It is very often bypassing the security review process. I just didn't want to generate all these things by hand. So we should take the genetic algorithm method if you're interested in really testing how robust your mechanisms are when you're leaning on whatever mechanism it is. See how aggressive a red team can be for you. So have your automatic red team perform a genetic algorithm to try to attack you in a controlled setting. This is not entirely new. There have been research papers a couple of years ago and last year as well, where it may not have been for code generation purposes, but improving the prompts that we give to an agent that will produce code is based on improving system prompts in general with a genetic algorithm. And the images here are just trying to give you a visual. Unfortunately, I learned just before the presentation that I cannot demo this live with the JavaScript application I created, but I think this illustration will do the best part. You might have two non-vulnerable samples that are not particularly good, or maybe the AI is very good at detecting that they're vulnerable. But if you have one that is successful in bypassing the security review, we'll take the rules that generated that particular one. Maybe the rules were rules J and K. So we're going to reuse rules J over here, rule K over here, because we're taking the best of these configurations for our adversary. And we eventually arrive, after successive generations, of finding the best rules in the rule set at something that achieves extremely high percentages. In fact, I got extremely high percentages with almost complete success all the time, 75% when I made the slide initially. And then I was just seeing a population that had a lot of different agents appearing with configurations that succeeded incredibly well to subvert the review process. Oftentimes people will write pass at something, meaning that the same sample or the same exact review was performed 7 times to see if any of them bypassed the reviewer due to the randomness. And so rather than just testing once, I was testing 7 times, and half of my samples for the top 4 agents were bypassing the security review process. That seems too good. Like, that's terrible. Why would the security review process be so brittle? It turns out that there's reward hacking happening. We're letting the agent improve itself, ultimately. It's just finding whatever is successful. So it decides to just be a nice little kid, and it decides not to write any vulnerabilities, which is why these things don't get flagged. So I had to introduce something more concrete to make sure that we're actually testing real vulnerabilities. So if you want to continue thinking with the black hat or the adversary, you might want to introduce SemGrep. They've actually put out a great paper exactly a month ago on the vulnerabilities that exist in secure coding review, secure code review with AI. And I just used their actual engine, which performs deterministic rules-based detection of vulnerabilities to filter out things that are ultimately not a real vulnerability. Sometimes SemGrep thinks something is a vulnerability, but I like seeing that it's low severity vulnerability thanks to their engine, and I can filter out stuff that is really not ultimately going to impact my organization. So Jinja2 means a user puts some input, it gets formatted for the screen. If there's not a lot of sanitization on this, it might not ultimately be the most catastrophic outcome, but it still could lead to some cross-site scripting in some cases. So generations on this screen are basically agents on the left generated with low performance. Over time, they improve over a few generations because the rule sets get better. And the curves that I was watching showed the same thing as the chart, where the population gets better over time. The probabilities are very high, but what SemGrep found is something I could corroborate. The percentages can be very high, but it also varies a lot. It's very inconsistent what you get from those security reviews. So defenders need to recognize that it's not perfect as a process to ask an AI to do the review. The real rules come from the SAST scanners like CodeQL, SemGrep. We have to put those in place without the LLM deciding whether to run it or not. And we should use this for defense, meaning the prompts that we use to ask our code review to happen can also be evolved with this genetic algorithm. When I ran this, I only get a couple of % improvements over what I get by default, but it is still something worth taking. I just haven't gone deep enough into exactly what ingredients can be available to these rule sets to test. So we should also do context evolution, which means not just asking the AI, here, I have some ideas, which ones are the good ones, but asking the AI, what other ideas are we missing, by reviewing and reflecting on the information that we could scan. So with elicitation, finding what the AI can bring for us is really valuable. That's my talk in a nutshell. We shift left for developers, but it's not the only control. We have to introduce or maintain, if you don't have them already, introduce them, but definitely keep the deterministic scans. And we can learn to do that in defense as well. Thanks very much.